Hello and welcome to our lesson on complex numbers in the complex plane, specifically in polar coordinates. This is going to be our trigonometry lesson covering section 9.3. And I've got four formulas here laid out for you. Let's go ahead and identify what they are. The first formula, z equals a plus bi. We call this the standard form. That is the standard form of a complex number in rectangular form. Okay, so we've got our standard form of a complex number in rectangular form. The second formula is also the standard form, and I'm going to abbreviate that this time. Standard form, but this is polar form. So we have two standard forms of a complex number. We've got rectangular form and polar form. And like in the previous lesson, I think in section 9.1, we said if there's two different forms, it's nice to be able to convert between the two. So that's one of the things we're going to be looking at, is how to convert back and forth between the two forms. There is also a third form that's called exponential form, and I will briefly mention it, but we're not going to actually include it in the examples. So just real quick, the exponential form would be r e to the I theta. And I want you to notice the correlation between exponential form and polar form. Polar form has an r and a theta. Exponential form also has an r and a theta. So it's real easy to go between those two because they both have r and theta. It's just a matter of replacing the r and theta in each formula with whatever they are. And so there's your exponential form. Now you've at least seen it. The third formula I have here is for the product of complex numbers in polar form, okay? So this formula will find the product, z times w, of two complex numbers that are in polar form. And if you notice what it says to do, this formula is just super easy. It says you're going to multiply the radii and add the angles. And that's pretty much it. So if you know how to multiply numbers together, and if you know how to add numbers together, then you can do this product formula. And the last formula is the power formula. You're going to notice up here at the top it says de Moivre's theorem. That's what this is. The power formula is known as de Moivre's theorem. And this is for raising a complex number in polar form to a power. And so what does that say to do? It says to take the radius raised to the exponent. The exponent in this case would be n. And the angle gets multiplied. So again, if you can raise a number to a power and if you can multiply numbers together, you can do this formula. Super easy. All right, now that we've covered the formulas, let's look at some examples. First example. Let's start with 4 minus 4i. This is obviously in rectangular form. We can see that a is 4 and b in this case is negative 4. And what they want us to do, two things. They want us to plot the complex number in the complex plane and then write it in polar form. So to plot a complex number in the complex plane is pretty much like plotting an x and a y in the rectangular coordinate system. So we said that the a is 4 and the b is negative 4. So the a would correspond to the x coordinate, 1, 2, 3, 4. That's 4 to the right. And the b would correspond to the y. And if you notice, the y is the I They rhyme. That's how you can keep them straight. Whichever number is the coefficient of I, that's your y. And that's going to be -4. And there's your point plotted. Now, notice this is not x-axis and y-axis anymore. This is the real axis and the imaginary axis. Since the number's complex, that's what we call the complex plane. You've got the real axis and the imaginary axis instead of x and y axis. All right, next thing they want us to do is write this number in polar form. And if you want to get polar form, you're going to have to find r and theta. And we're going to recycle some formulas that we've covered previously. I think in section 9.1, we talked about that r is the square root of x squared plus y squared. But in this section, it's going to be the square root of a squared plus b squared. And so that's how we're going to get our radius. And our theta is going to be the inverse tangent of b over a. That's how we're going to get r and theta. And so let me slide this over just a bit. And we'll do plug and play. For the radius, we've got the square root of 4 squared plus -4 squared. That's going to be 16 and 16, which is 32. And to write that in simplest radical form, that is going to be 4 square root of 2. And the professors or the homework system, most people are going to want that value to be exact, which means not a decimal approximation. So we want to leave that 4 square root of 2. That is the exact value. For theta, we're going to need the inverse tangent of -4 over 4, which simplifies to the inverse tangent of -1, which I believe is -pi over 4. And I don't know if you noticed, but when we plotted that point, did you notice it landed in quadrant 4? And the angle that we came up with, -pi over 4, is also in quadrant 4. So that makes us feel really good about that angle. Remember, negative angles go clockwise. And so that's going to be -pi over 4. And then the 4 square root of 2 is the distance from the center out to that point. In other words, that would be the radius of the circle that goes through that point. Now, this is not the answer. This is the numbers that we need for the answer, the actual answer. Remember, we're trying to write this in standard form. And standard form of a complex number is r cosine theta plus I sine theta, where our radius is 4 square root of 2 cosine of, and our angle is -pi over 4. And I got to tell you, I'm not real happy about putting a negative angle in there. I usually like the angles to be positive. And so can you tell me what would be the positive equivalent to -pi over 4? What would that angle be if I spin clockwise around to quadrant 4? Well, that would be 7 pi over 4. Now, what am I trying to say here? I'm trying to say I feel better about having a positive angle. If you write it with -pi over 4, it's not wrong. It's just not right, okay? You can put the -pi over 4 in there and it would be correct, but I feel that this answer is better. And there's our first example done. A rectangular complex number plotted and converted to polar form. I think we should do another one. Let's move on and do another example. All right, same song, second verse. We have another complex number in rectangular form. we want to put the dot in the right spot and then convert it to polar form. So here we can see that A is -2 and B is 3. And so if I'm going to plot that point in the complex plane, that's going to be -2 to the left, up 3. And can you see that that point lands in quadrant 2? Yeah. So there is the dot in the right spot. Now we need to calculate the radius and the angle so we can convert to polar form. That's going to be the square root of -2 squared plus 3 squared. 4 and 9 is 13. And that is exact. I'm going to leave that square root of 13. Theta, my angle, is the inverse tangent of 3 over -2. And I'm going to have to go to the calculator for that. So, pulling up the calculator, what do I want the answer to be? Radians or degrees? Let's go with degrees this time. Does it specify? It doesn't specify the instructions. We're going to go with a degree this time. Let's say inverse tangent of 3 divided by -2. Notice I'm using the divided by symbol instead of the fraction button this time. That's perfectly fine. And that's going to give me -56.3 degrees. And they'll have to tell you where to round to. I'm going to round to the nearest tenth in this case. -56.3 degrees. Now, what I want you to notice is that this angle, since it's negative and acute, is going to be a quadrant 4 angle. That is not going to line up with the angle that we need to get us into quadrant 2. In fact, if you notice, if you look at this, you'll see that it's 180 degrees out of phase with the point I plotted. And this should kick you back to a previous lesson where I talked about, I said, if x is negative, you have to add 180 to theta. Okay, so the same thing applies here. If you want the correct angle and your A happens to be negative, you're going to have to add 180 to theta. That's what you have to do anytime A is negative to get the correct angle. So let's pull that calculator up one more time and add 180 to theta. And we need 123.7 rounded. 123.7 degrees. There's my theta. And now we can finish it off. We can write the answer in polar form. That's going to be R cosine theta plus I sine theta. And if you want to put, let's put the degree symbol to make it perfect and put a box around that because we're done. And I think the last thing I'd like to do is show you that if you have my particular calculator, there is a way you can check and see if this is correct. You can actually input this entire answer into the calculator and see if it gives the problem back. Now, we are going to need to be in complex mode since this is a complex number. So we're going to go we're going to go menu over to complex, which is number 2. And if you see on the calculator up here, now there's a little I, which means we're in complex mode. And we should be able to type in this answer just the way we wrote it, making sure we're in degree mode. Closing the parentheses appropriately. And then for the I, that's the ENG button. I sine 123.7. Now I'm going to need double close parentheses, once for the angle. Do you see that? Once for the trig function. And then this close parenthesis corresponds to this close parenthesis here. Now, look what it gives me. It gives me negative 2.000. That rounds to negative 2. For the real part, that is my A value. And if I scroll over, you're going to see 2.999, which rounds to 3. 2.999 rounds to 3. And that is my complex part. In fact, if I keep scrolling, you're going to see the I there. So that is a way that you can use the calculator to verify that your answer is correct. You got to be in complex mode so that you can input the I, and you input your answer to see if it gives you the problem back. And remember, it's not exact because we had to approximate this angle here. Cool. All right, I hope that was helpful. Let's jump to another example. I've got several examples I want to look at in this lesson. And this time we're going to have 2 cosine of 2 pi over 3 plus I sine 2 pi over 3. And I think it's pretty obvious that this is a complex number in polar form. Okay, here we go. We know this is complex because it has the imaginary I. And if I write the formula above this, this is R cosine theta plus I sine theta, where I can see the radius is 2 and the angle is 2 pi over 3. So this is definitely a complex number in polar form. And they want me to convert this into rectangular form. Okay, this may be one of the easiest things you'll ever do. To convert this to rectangular form, all you have to do is take the radius and distribute. So that's going to give us 2 cosine 2 pi over 3. That will be my A plus, remember I said we're going to distribute the 2. That'll be 2 sine 2 pi over 3. And then the I, I'm going to stick at the back. And this will be my value for B. And at this point, you can either use the unit circle and find the x coordinate and the y coordinate at 2 pi over 3, or you can use the calculator, which is what I'm going to do, but I do need to be in radian mode. All right, so let's go shift, setup, angle, radian, 2 cosine 2 pi over 3 works out to be -1. And then let's do the other calculation, which is super easy. Watch this. Back. And let's delete the cosine and insert the sine. Super easy. Square root of 3. Positive. Square root of 3i. Hey, look at that. We're done. That is now the complex number in rectangular form. And if I wanted to, I could plot it. I think I'm going to do that just for fun. Negative A, -1, positive B, and I happen to know that square root of 3 is about 1.7. So that's going to be about there. And notice what this tells me. It tells me that I should feel good about this answer because that is the quadrant that this angle is in. 2 pi over 3 is in quadrant 2. And the radius is 2 units, 1, 2. So if I look at plotting this angle and then plotting this rectangular complex number, they're going to plot in the same spot. And that means that I've got the right dot. Okay, let's try another example. And this time we're going to say z equals, z usually means a complex number, 2 cosine of pi over 8 plus I sine pi over 8. Now that's a complex number in polar form. And then guess what? They're going to give me another complex number in polar form. That's going to be 2 cosine pi over 10 plus I sine pi over 10. And here what they want me to find is the product. It says find the product of the complex numbers. And it says write each answer in polar form. Lucky for us, they're already in polar form. So we can scroll back up and look at our formula if you want to. To find the product, it says we need to multiply the radii and add the angles. Super easy. We're just going to multiply the radii and add the angles together. And this is where I got to say product means stack them. Product means stack them. If you stack them one on top of the other, it lines up the pieces that go together. So the 2's, those are the radii. 2 times 2 is 4. Cosine of, and then we're going to have to add fractions that do not have a common denominator. So in order to add pi over 8 and pi over 10, you're either going to have to use your mental skills and get a common denominator, or if you're like me, you're just going to bring up the calculator, okay? Pi over 8 plus pi over 10. And some people may argue that it takes longer to type it in than it does to do it by hand. What I like about doing it with the calculator is it takes out the human error. If I know how to input it correctly, I'm not going to make a human error, and it's going to give me the answer reduced to lowest terms. So the answer for our angle is going to be 9 pi over 40. And the cool thing about this is I only have to do that one time because these are going to add and make the same value. Bam. Hey, and guess what? We're going to put a box around that because we're done. That is the product of the complex numbers in polar form. If they would have said convert to rectangular form, that would be super easy also. You would just distribute the 4 like we did in the previous example, and then grab your calculator and calculate your value of A and B, just like we did before. So you do want to make sure you read the instructions and give the answer in the form requested. And I've got one more example, and we're going to call it good, okay? Last example, square root of 3 times cosine of pi over 18 plus I sine pi over 18. And all of that raised to the 6th power. And so this example is going to be taking a complex number in polar form raised to a power. This is going to be de Moivre's theorem. And so if you recall what de Moivre's theorem said, it says whatever the exponent is, that's going to be your value for n, and you're going to take your radius, which is square root of 3, and you're going to raise it to the power, but your angle gets multiplied by the power. That's what de Moivre's theorem says. The radius gets raised and the angle gets timesed. And since they gave us nice numbers, this is going to be super easy. Okay, so doing square root of 3 to the 6th, let me show you the long way to do that. Square root of 3, 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 square root of 3. Bop, 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 bop. Really, that's what that means if you do it the long way. And each pair would produce a square root of 9, which is 3. So really, you're going to have 3 times 3 times 3, which is 27. Now, that's how you would do that if you were stranded on a desert island with no calculator. You can also pull up the handy-dandy calculator and type in square root of 3 to the 6th, and it will verify your 27. So you can do it manually or electronically. And the 6 and the 18 are going to reduce. Those are super nice. 6 goes into 18 3 times. And so that's going to reduce to just pi over 3. All right, so if it said write your answer in polar form, we would be done. This is polar form. Unfortunately, it says write your answer in rectangular form. But remember, that's not that big of a deal. We just need to distribute the 27. That's going to give us 27 cosine of pi over 3 plus 27 sine of pi over 3. This is my A. This is my B. And then don't forget your I at the end, okay? And then from here, you can look up the x coordinate at pi over 3 and the y coordinate at pi over 3. Or you can use the calculator, which is what I'm going to do. 27 cosine pi over 3. And I'm in radian mode. Oh, 27 halves. I wonder if it would take 13 point. Well, 13.5 is exact. It's a decimal, but it's exact. You know what? But I like it effed up. I'm going to leave it improper. That's the way I like it. 27 halves. And I reckon that that's going to be 27 square root of 3 over 2. That's what I'm guessing. Let's see here. Delete, and let's do sine. 27 square root of 3 over 2. And I think we're done. This is now rectangular form. Okay, polar form, rectangular form. Make sure you know how to go back and forth between those two. And I think before I cut you loose, let's do one other thing just to show how freaking sweet this calculator is. Now, I'm not sure it's going to do this, but I think it may. I'm going to try to type in the exact problem the way it looked at the beginning and see if it will give me the answer, like skip all the work. I'm not sure if it'll do it. Let's see if it will. Square root of 3 cosine of pi over 18 plus, and I'm still in complex mode, so I can say plus I sine pi over 18. Move out. Now, how many closed parentheses do I need? There's one for the trig function. Okay, let's see, back up here at the top. This parenthesis is for this parenthesis. Okay, so I've got 1, 2, and then a parenthesis for this parenthesis, so I need to close that. And then the bracket is another parenthesis, so I need another parenthesis, and then to the 6th. Look what it did. It gave me the 27 halves, but this, it did not give me the exact value. It rounded that, 23.38. Let's see if that is 27 square root of 3 over 2. 23.38, is that 27, whoops, I hit cube root, square root of 3 over 2. 23.38. Okay, so the calculator did give the right answer, but it did not give exactly. It gave the decimal approximation, and so the calculator is not going to do all the work for you and give you the answer you need. It will verify this answer, but it will not give you this answer. And so that's why using a calculator is nice, but it's not going to solve all of your problems for you, okay? It'll help you. In some cases, it does all the work, but it's nice to know how to use it and at least verify your answers, okay? So that's going to do it for this lesson. If you have any questions or comments, feel free to leave those in the comment section below, or you can text me. And thanks for watching.